Alright, so we're going to talk about a use of the log and exponential equations that we've talked about in this chapter. It kind of all builds up to this conclusion, but it's all going to be stuff that we've actually already done. So there are two types of exponential functions. We have the growth and the decay. The common equation is a decay, and they use half-life. So the half-life of a radioactive substance is the time it takes for half of the atoms to go away, to break down. Hopefully not from science. If not, then you learn something science in math. This is why when the nuclear reactors have melted down in the past, or the nukes that were dropped, people have thrown a big deal about it because the radiation does not go away. Actually, if you test things in the atmosphere now, you can detect some radioactive material ever since 1939, whatever they, not 39. It's something like that, though. It's earlier than you think it is, but the first nuclear test. So, anyways, getting back to this problem, if we know the half-life is 24,000 years, first you have to find the value of k. So, when we find the value of k, all we have to do is take, and I'm going to use p instead of a. I think I have a up there, but p is my starting amount. Well, if I don't really care how much I start with, I can say I start with 1 gram. Okay, e to negative kt. And obviously you don't need the negative because when I put a half over here, because it's half-life, so I only have half of it left, when I put the half there, that's already half of this, and it's going to make that negative. So really the negative is redundant. So we can divide by 1, but the 1 is really kind of not necessary, so we can ignore it. To get rid of e, all we do is ln. Oh, and this should not be t. This should be how many years it takes me, which is 24,000 years. Sorry, I got distracted. When I do the ln, that makes the e go away, and the ln, so I get k times 24,000. So now I'm going to divide by 24,000. And I'm going to grab the calculator on this thing to do it, because it's easier that way. That way you can see me type it in. So I'll go down here. Calculator, it's probably not going to work. Thought so. So I will close it and open it again. So I go ln of 0.5 and then divide that by 24,000. Hopefully you see that ln on the left side there. Now something to point out here. Notice it says e to the negative fifth. That's like saying 10 to the negative fifth. Meaning, in terms of k, this value is actually 1, 2, 3, 4, 5. So 4 zeros, 2, 8, 8. I'm going to leave that as my rounding. So I would take that answer, and a lot of times it'll be a part B. They'll say if I have this much, you'll have more in a little bit. But the important thing is for this equation, we'd have one that was E 00288T. That's usually your part 1 at least. So we're going to do this again using the 5,730. So set up the same way. 1 equals 0.5 because we're talking about half-life again. E to the k times 5,730. The ln will cancel that. You'll notice that all these equations have the same sort of thing on the side. They don't always look this way, so I'm not going to say you have to do it every time. But a lot of times when they give you the they give the half-life, this is how you have to start them usually. So once again, I will go ahead and use the calculator on here, which already crashed again because the calculator on the computer is not as reliant as me. So ln 0.5 divided by 5,730. So I end up with an equation of E 1, 2, 3 zeros, because it's 4 now. Once again, to explain that, this one looks like this again. One, two, three, 4. So that's how I got this equation up here. Okay. Going on. We take that equation This is the part B. Take that equation of E negative 0.00. Ooh, I already forgot what it was. And I'm going to use my calculator to double check what I had before. So it was 0.00121 that I used times t, because I know how many years. And then it says if it started with 42 and now equals 8, we have to solve for t to find out how long ago it was alive. So, divide by 42. So that gets me 0.19047. Once again, more decimals the better. How do I get rid of E? ln. I'm going to do it on my calculator here. That equals negative 1.626 equals just this. So I have to divide that by the negative 0.1230121, which means that approximately 1,300. Wow, I said that wrong. 13,704 years ago, this fossil would have been alive, according to Half-Life. Okay? A common exponential growth would be bacteria. They also do it with people and rabbits. I've seen rabbits a lot. Once again, same sort of problem. You start with a given amount, 1,000. And they will give you a time. In this case, it says 40. And say after that amount of times, there's this much. Find the K value. And so then we do ln. Gives me 0.50078. Divide that by 40. And we find a growth rate of that. So go back and write your equation again. And there's my equation. Technically, if I had 1,000, I can put the 1,000 back in front again. Okay, clearing that. Looking at the next one. Suppose a second type of bacteria is growing exponentially according to the model, blah, blah, blah. Determine how long. Oh, so I have this one up here, which I shouldn't have done what I did. So I'm going to take this equation here. Copy it now. I'll clear that. And this would be equal to this new equation. So, first thing, we want to know when this group will be more is what it said. So, divide by 50, divide by 50. I get, what, 220? Okay. Now what do we want to do? Well, only one thing we can do is put the natural log on here. And do remember I can split this into addition when I do natural log. Ooh. Might be hard to read. Let me make it a little bigger. So I end up with natural log of 20. And I'm going to subtract this one over here. Notice once again that those cancel, so I actually end up with this minus. So I'm going to check it on my calculator. So now it's log of 20, then needs to be divided by this. And you find out that after, are we talking hours or days? Minutes. That after 97 minutes, T, actually if we round up, should have been 98 minutes of time, there would be more in this new group than in that first group. Another type of exponential equation that you could see is this one. They're limit functions because they have a limit to how much they can hold. I'm just going to sketch the graph for you. The graph would simply look like, whoa, my iPad's messing with me. Okay, so you would have, as far as the graph goes, we only really care about the positive quadrant, right? As the top gets bigger, or as the bottom gets bigger, the top's actually, the whole equation is going to reduce. So it's going to look like that at first. Okay? So what is the horizontal asymptote? That's not right. Let me check this out real quick. Oh, so if I plug in 0 for t, I'm going to end up with 1880 divided by 2.42. Meaning, at 0, I'm at 776. Okay? Then as time goes on, since, if you look real close, that's a negative power, this is actually going to be getting smaller. As the bottom gets smaller, this top will actually increase. So, the equation will actually go like this. And even though you can't see it, this graph will slowly approach whatever this top number is. That's how these graphs work. That top number is the limit to how high they can go or how high they can start. So the maximum population is 1880. The horizontal asymptote, which we haven't talked a lot about, would also be 1880 because it's that straight line right there. Okay, I'm going to stop there. I think I'm probably short on time. If you have any questions, you can always email me or come see me. Otherwise, have a good evening, and I will see you soon.